Hello and welcome to this lesson in our study of linear algebra. Okay, in this lesson we talk about inner product spaces and their properties. Okay, so let's choose any two vectors u and v. Okay, choose any two vectors u and v such that these two vectors they have finite number of elements in them. That's two vectors of finite dimension. Okay, so our u be we let our u be u1 up to un, and our v be v1 up to vn. Okay, then the inner product of these two vectors is given by u dot v, okay, which is the same as u transpose v. Okay, so that's what we have here. That's u transpose, that's v, and this is given by u1 v1 plus u2 v2 up to un vn. Okay, so now we have a typical example. Let our u be this, that's 2, -5, -1, and our v be 3, 2, -3. Then the inner product of u and v, that's u dot v, is given by u transpose v. Okay, and this is the same as, you see, our u is 2, -1, -2, -5, -1. So u transpose v is given by 2 minus 5 minus 1 multiplied by 3, 2 minus 3. Okay, so when we solve this, 2 times 3 is what? 6, minus 5 times 2 is 10, minus 5 times 2 is -10, plus 3. Okay, and when you simplify this, you get -1. That's what we have here. Then v dot u, you also, when you solve that, v dot u is given by v transpose u. Okay, when you simplify, you get -1. So this means that inner products are what? Commutative, or in other words, commutativity of the inner product holds in general. Okay. Now let's continue. Let's look at some basic properties of inner products. So now, first one, when you have u and v be vector spaces, okay, such that all the elements are real numbers, the elements in them are real numbers, and these vectors are also finite dimension. Okay, then inner product of u and v is the same as inner product of v dot u, and it can also be written as uv or vu. Okay, also that's a commutative property or commutativity of inner product. Okay, now we also have u plus v all multiplied by w. Okay, and this is also you can expand brackets. Okay, so this can also be written as uw plus vw. Okay, and it's equal to the inner product of u plus v and w. Okay, they are all the same. That's the distributive property. Okay, then when you have any constant or any scalar c, okay, then the product of the scalar and the vector v all multiplied by w can also be written as this, and is the same as this. Okay, then this is supposed to be a different property. Okay, that's the norm of a constant c and vector u is the same as absolute of scalar c and the norm of what u. Okay, and you should know that always the inner product is always non-negative. Okay, it cannot be positive. Okay, so it's either 0 or greater than 0. It is 0 if and only if what the inner product if and only if vector u is what is a 0 vector. Okay, now let's move on to the norm of a vector. So now let's choose a vector of finite dimension v, okay, with all the entries being real numbers. Then the norm of this vector is the same as the Euclidean norm, since all the entries or all the elements of vector v are what real numbers. Okay, and Euclidean norm is the same as the L2 norm. Okay, it's the same as the L2 norm. So the norm of this vector is given by this. Okay, that's the norm of vector v. We are using the Euclidean norm because all the elements in v are what real numbers. Okay, and the Euclidean norm is the same as the L2 norm. Okay, so now let's choose our vector. These 2 dimension. Okay, then the norm of this vector is given by this, right? That's 3 square root of 3 squared plus 4 squared equals to 5. That's the norm. So the norm of this vector is what? 5. Okay. Yeah. So now let's move on. Okay, so let's suppose that our v is 2 dimension. That's vector, that's v1, v2. Then we can identify v as a geometric point in the plane. Okay, then the norm of v coincides with the notion of the length of the line segment from 0 to v. Okay, so this simply means that norm actually measures its distance from the origin. That's what we mean. Norm measures its distance from the origin. There is a difference between norm and a metric. Metric measures its distance between 2 vectors. Once again, metric measures its distance between 2 vectors, but norm measures its distance from the origin. Okay, so we are dealing with norm, so we are definitely going to measure a given vector from the origin. Okay, that's what we mean. So you see, for the diagram, that's v1, v2, that's vector. So this is what v1, this is v2. And you realize that this line, the vertical line, is perpendicular to the horizontal line. So you form what? A right angle. Therefore, this is what we have, our right angle triangle here. And from the Pythagoras theorem, the side that's opposite to the right angle, for any given right angle triangle, the side that's always opposite to the right angle is actually the hypotenuse. Okay, and the hypotenuse is the square sum of squares, okay, of the other 2 sides. Okay, is the sum of squares of the other 2 sides. So this is the hypotenuse. Okay, that's the hypotenuse. So from Pythagoras theorem, when you have a product of a scalar c and a vector v, is the same as the absolute of c times the norm of v. E times the norm of v. Okay, so a vector, you see, we have a unit vector. I hope you have heard about it. Unit means 1. Okay, so when you have any vector with a length of 1, then you can see that that vector is what? A unit vector. Okay, so when you have any vector, you can and they are not unit vector, you can what? You can express it as what? A unit vector. Okay, so for instance, when you have vector v, okay, such that v is not a unit vector, you can find the unit vector of v, okay, and the unit vector of v is given by u and is the same as v over the norm of v, okay, v over the norm of v. And the process of creating the unit vector is the same as what? Normalizing what? V, okay, and you can also say that u, which is the unit vector of v, okay, is in the direction of what? V. Okay, so let's look at this example. So you have v to be 1, -2, 2, 0. That's 4 dimension. Then we are to find the unit vector u in the same direction as what? V. So now our u is given by what? Vector v over the norm. Okay, so first of all, we have to find the norm of the vector v. So the norm of the vector v is given by this. You see, all the elements in v are real numbers. Okay, so we find the Euclidean norm. So that's what we have here. Okay, have 3. So we get 1 over the norm of v times v. That's 1 over 3 times vector v. There's supposed to be 0 here. Okay, can make that correction. So when you simplify this, you get this. So this is the unit vector. If you want to check your answer, you can normalize this newly generated vector u. Okay, when you do that, you get this. Okay, this shows that our newly generated vector u is what? A unit vector. It has a norm of 1. Okay, it has a norm of 1. So now let's look at definition. When you have any two vectors u and v, and such that u is given by this u1 up to and v is also given by v1 up to vn, then the distance between these two vectors is given by this, and you can also call it as a metric. Okay, metric, that's what? uv. Okay, I previously said in the earlier, I said that norm measures its distance from the origin. Okay, whereas metric measures its distance between 2 points. Okay, so now, or it measures its distance between two vectors. So now we have two vectors. Okay, and so when we have these two vectors, you can find the distance between these two vectors, and you can also call it as what? A metric, okay, of vector u v, and it can be written as d of what? uv. Okay, so it's given by this formula. So when you have, let's say, two vectors u and another vector v, then the metric or the distance between these two vectors is given by this. So first of all, you find the distance u minus v. That's 7, 1 minus 3, 2. When you solve this, 7 minus 3 is 4, 1 minus 2 is -1. Then you find the norm of the result, so you get root of 17. Okay, that's the distance between two vectors. Now let's solve this exercise. Okay, so you can pause the video and try your hands on these questions. Okay, now we have we're given vector u to be 2, 3, 2, -1, in another vector v 4, 2, 1, 3. Okay, so first of all, we are to find the norm of each of the vector. Okay, so before then, let's talk about p norm of a vector. So let v be any vector such that v is given by x1 up to xn. Okay, then the p norm of this vector is given by this. Okay, so this is the general definition of what a p norm. Okay, so now let's choose each vector. We have two vectors u and v. Okay, but you realize that all the elements in each of the vectors are real numbers. Okay, and since the elements of each of the vectors are real numbers, then we find the Euclidean norm. Okay, so the Euclidean norm is the same as 2 norm. Okay, so this time around our p is equal to 2. Okay, so you have 1 over 2. Okay, so it will be x1 squared plus absolute of x2 squared plus absolute of x3 squared up to the absolute of xn squared all to the power half. Okay, that's L2 norm. Okay, it's the same as the Euclidean norm. So the norm of u is given by this. That's the absolute of 2 squared plus absolute of 3 squared plus absolute of 2 squared plus absolute of negative 1 squared, or under a square root, or all to the power half. That's what we have. When you simplify this, you get 3 root 2 units. Okay, you get 3 root 2 units. The same thing applies to the norm of v. So that's absolute of 4 squared plus absolute of 2 squared plus absolute of 1 squared plus absolute of 3 squared, or exponent half. And when you simplify it, you get root of 30 units. Okay, then the next one, we were required to find the distance between these two vectors. Okay, so the distance between these two vectors is given by, that's the metric. Okay, and that's the norm of u minus v. Okay, so we have u, we also have v. So u minus v, you can do it other way around, it's still the same. You can make it the norm of v minus u. Okay, you see, when you have 2 points, u and v, and you want to measure distance, you can stand at u and measure a distance from u to v, or you can begin at v and measure distance from v to u. They are the same. Okay, so instead of u minus v, you can also make it v minus u. They are all the same, right? So now u minus v is given by this u. So you have this 2, 3, 2 minus 1 minus v, that is 4, 2, 1, 3. Okay, so we have 2 minus 4 is minus 2, 3 minus 2 is 1, 2 minus 1 is also 1, then minus 1 minus 3 is minus 4. Okay, good. So this is what we have. This is what you get. Okay, that's u minus v. Okay, that's u minus v. So that's what we have here. 2 minus 4 absolute all squared. Okay, that's what we have here. Okay, so 2 minus 4, absolute of 2 minus 4 is negative 2. Absolute of negative 2 is 2. When you square it, you get 4. Okay, 3 minus 2 is 1. Absolute of 1 is 1. 1 squared is 1. 2 minus 1 is 1. Absolute of 1 is 1. 1 squared is 1. Negative 1 minus 3 is negative 4. But absolute of negative 4 is still 4. So 4 squared is 16. So when you simplify this, you get 22, square root of 22 units. Okay, that's the distance between the two vectors. Okay, so now let's move on to the last one. We were required to find the angle between two vectors. Okay, so now this is a formula for finding angles between two vectors. That's called theta is given by the inner product of the two vectors divided by the products of the norms of these vectors. Okay, so when you have two vectors u and v, then the angle between these two vectors given by cos theta equals to u dot v over the norm of u times the norm of v. Okay, so first of all, we need to solve for u dot v. U dot v is u transpose v, and this u transpose, and this v. Okay, so this is given by 2 times 4 is 8. That's what we have here. Plus 3 times 2 is 6. Plus 2 times 1 is 2. Plus negative 1 times 3 is negative 3. Okay, so when you solve this, 8 plus 6 is 14 plus 2, 16 minus 3 is what? 13. Okay, so now we can substitute it here. You see, u dot v is what? 13. The norm of u is what? 3 root 2. That's what we have here. Times the norm of v is root of 30. Okay, so that's what we have here. So theta is the same as the cos inverse of this. Okay, and we get what? 58.98 degrees. This have been approximated to 2 decimal places. Thanks for watching.